All right. Well, as I mentioned, my name is Jaron Krogel. I actually work here at the National Lab. I'll be giving you guys an introduction today to the NEXUS workflow automation system. It's a code that I've been developing over the last several years to help kind of speed up the work that you do with QMC Pack. To give you a little bit of an overview of what we'll discuss, first I'll give a brief motivation for scientific workflow automation tools. Then I'll give information in general about NEXUS, which is a workflow tool designed specifically for QMC Pack and all the codes related to it. I'll give a brief overview of what it's like working with NEXUS from a user perspective, leading up to the examples. I'll give an overview of the workshop examples themselves and give some idea of where you might go for additional resources about NEXUS and future directions. Please interrupt me at any time during this talk if you have questions. I'm anticipating there'll be plenty of time for that. If we do have remaining time in this block at the end of the talk, we might just go straight into the workshop examples, and I'll be on hand for question answering at that point. All right, so what about scientific workflow tools? I would say that scientific workflow automation tools have grown in popularity in recent years. Some examples of these you might be familiar with. It's possible to remove the signal at the bottom. For example, A-Flow or Fireworks, which is associated with the materials project. Also, the atomistic simulation environment. What these workflow tools do is they generally give the ability to perform high throughput calculations. This is particularly the case for A-Flow and Fireworks, or to simplify the calculation process to make everything more productive. A lot of people use ASC for that reason. And I would say that the growth and popularity of these tools indicates the usefulness of this approach. But these existing tools primarily favor DFT codes with an emphasis on VAST. So what about Quantum Monte Carlo? Quantum Monte Carlo has a couple of unique challenges, I'd say, from this perspective. One is that we actually spend a whole lot of time focusing on control of systematic errors. There are many things to converge. For example, production QMC results require many subcalculations for this reason. You have to converge a number of parameters, maybe the plane wave energy cutoffs for your orbitals or the basis set, spline grid sizes, and if you're under boundary conditions, K-point grids, supercell sizes. Making sure that your wave function is fully optimized might take multiple steps. DNT time step extrapolation. Also, along the way, you often consider many alternatives and possibly execute more than one. For example, trial wave function choice, the level of DFT functional, or the level of quantum chemistry. You often are performing calculations that start from many of these different positions. Also, pseudopotential choice, locality versus T moves. You'll often end up rerunning large portions of the calculation in a similar fashion, exploring these options and choices in your study. Overall, this amounts to a great deal of work, and in my experience, and probably yours too, QMC just takes more human time than if you were to do a more straightforward, say, DFT study. And this is something we'd like to improve. Also, this complexity adds a fairly high barrier to entry for newcomers. This is true at the level of the theory, which is more complex, but it's also simply true at the level of working through all of the calculations you have to do to get it right. So we'd like to improve in both of these ways. Another challenge for QMC, it's not totally unique, but there tends to be a fairly deep hierarchy of machines that you work on, right? You're going to do some calculations on a workstation, maybe you're going to do some orbital generation with DFT or Hartree-Fock, some quantum chemistry methods. You might move up to an institutional cluster, say to do wave function optimization, and then finally you're going to end up at some maybe leadership computing facility to do production diffuse Monte Carlo calculations, and then back to the workstation for data analysis. And this again just adds to the complexity of what you're doing and how you have to manage all of the information necessary to get it done. So working on these multiple machines adds complexity. Having to do monitoring of your jobs on all these queues, for example, adds to the human time. So we'd like to improve both of those. All right, so general information about NEXUS, what it is. So we've developed a QMC-centric workflow system to address these needs. Its goals are to make, can I go back one? Thanks. are to make QMC calculations more accessible, so a less steep learning curve for new users. I found this bears out in practice. We've got a number of postdocs at Oak Ridge who have not had any QMC background, but this has helped them to get up to speed more quickly and do correct calculations sooner. We'd like to automate all the time-consuming steps in the QMC simulation process. Also like to enable large-scale job submission on a variety of supercomputing platforms, so it'll be closer to being just as easy to work on a supercomputing environment as it is on a workstation. To make these simulation workflows scriptable, so you can easily do, say, scans over different kinds of wave functions, different DFT functionals, etc. And in general, to support every type of calculation possible with QMC Pack and provide documented examples. I'd say this is still aspirational, but at this point support's pretty broad. All right, so core features of NEXUS. NEXUS provides a simple Python interface for workflow composition. This user input script acts as kind of a meta input file for the execution of all the simulation codes. For its simplest examples, and all the examples today in the workshop, it actually does more or less resemble an input file. It looks a lot like just a list of keywords and parameters that you're setting, and that's it. One advantage to this is that it brings all these various simulation programs that vary quite a bit in their idiosyncrasies and how you work with them together into a single coherent framework. One key feature of NEXUS, like essentially all other workflow automation systems, is it supplies input file generators. So you have automatic input file creation from the minimal user inputs. NEXUS provides job monitoring, so you automatically execute simulation workflows and monitor them for completion on your behalf. So what you end up with at the end is the final result without having to spend a lot of time babysitting queues and so forth. It also provides analysis capabilities, so extraction of simulation results that are also accessible within this same user script. This is, I'd say, more relevant for supporting codes like DFT codes and such, where QMC you still spend a lot of time processing with command line tools. It's more complicated to work with due to its statistical nature. So that's more true of those codes. Okay, so what does workflow execution and monitoring look like with NEXUS? I've said the word workflow a lot. What do I mean by that? So for example, I show here what might be a DMC calculation of bulk diamond in a very simplified way. So you're going to start with an SCF calculation, maybe with quantum espresso. You'll convert the orbitals with PWD QMC Pack. Next, you're going to do Jastrow optimization with QMC Pack, and then finally DMC. So these little blocks here represent separate simulation runs, and the arrows represent data dependencies. So for example, here you're passing orbitals to be converted and orbital information onto QMC Pack, and also Jastrow information onto DMC. So NEXUS handles both the execution of these individual blocks, but also the data dependencies in between them. So for example, it will select the optimal Jastrow for you and allow you to run DMC. How are the workflows themselves executed? Well, let me illustrate that with probably a more realistic or interesting example. So this is a slight expansion on the prior example. So here's the bulk diamond workflow again, just on this left-hand side. But now I'm imagining that I've done everything I need to do to start doing a production calculation of, say, a defect formation energies in diamonds. So you want to do bulk, but also the T, H, and X interstitials, where in the end you want 4 DMC energies, one for bulk and then one for each defect at a relaxed geometry. So you're going to do structural relaxation, SCF for the orbitals, conversion step, and you are going to optimize the Jastrow for bulk, but you might also want to use that as a starting point for each of the Jastrow optimizations you're going to do for the defects. So how is this as a workflow going to be executed by NEXUS? What NEXUS does is it will execute all independent parts of the workflow in parallel. So for example, at the first step, when NEXUS begins running, when you start running this NEXUS user script that does this, it will submit jobs for the bulk SCF and all of these relaxed calculations at the same time. It can also manage an arbitrary number of these workflows at the same time. If you had multiple structures, multiple systems, you could run them all within a single script, and it would submit jobs in a massively parallel way, say on the supercomputing environment you're on. Okay, so how would this proceed? So first, probably the SCF would finish on bulk. You'd enter the conversion step. That would finish, and it would submit a job for wave function optimization. Probably at that point, the relaxation runs would be done. The SCF jobs would get submitted for each of them. Next, they would complete, and quickly you'd have an orbital conversion step for all of them. Following that, you're probably still waiting in time for this optimization run to finish with QMC pack. That's going to be by far the heaviest part. But once it's finished, all of the other optimization runs will begin, and also DMC because it's independent. Finally, the other DMC runs will start. This DMC run will finish, and all of these will too. Okay, and then at this point, what if you wanted to add to this? So, for example, you were informed by somebody that you used tmoves version 0 in DMC, and you want to use the size consistent one. You could just add a single DMC calculation here, and NEXUS, if you reran the script, would skip all of the steps that it's done already and just execute the portions that you've been adding. Or perhaps you could change which DFT function you use to relax, or which DFT function you used for the orbitals, and rerun the script again, and it will just do everything in between. Okay? All right, so that was an example just with Quantum Espresso, what codes are supported. So, of course, we support QMC pack and Quantum Espresso. We have explicit interfaces to games, PyCF, Quantum Package, and VASP, and handling all the data dependencies between them and QMC pack. So what type of calculations are supported? Of course, with QMC pack, you can do wave function optimization and all the real space methods at this point. With Quantum Espresso, there's support to do SCF, non-self-consistent calculations, structural optimization, all of the post-processing tools, and orbital conversion. With VASP, you don't directly feed orbitals from VASP into QMC pack, but you can do structural optimization and nudged elastic band and feed that information in. Similarly, we have support for games, PyCF, and Quantum Package for all the different types of wave functions that can be generated, whether single determinant or multi-determinant, including selected CI. For convenience, NEXUS has specific implementations for different machine environments. This allows you to kind of get around needing to work heavily with the sysadmins of those machines and have them go through some difficult, painful install process while still dealing with the idiosyncrasies of those machines. So right now we have support to work at Oak Ridge, Argonne, Sandia, computers at NERSC, Illinois, and TAC. And probably most of you will have access to a machine somewhere in here in addition to an individual workstation. It is fairly straightforward to extend to new machines. If this is something you're interested in, contact me. I will work with you directly to get whatever machine you're on supported. So where has NEXUS actually been used? Here I provided a list of just ones I was able to find of projects where NEXUS has been used in recent history. You'll notice that on a number of these works, you'll see a lot of transition metal oxide species. Probably the majority of transition metal oxide calculations that have been done with QMC pack have used NEXUS. But in addition, more recently, we've been doing more calculations that depend on Gaussian codes, such as games. We did benzene structural optimization using Gaussian process. And we have works in progress using both PySCF and Quantum Package. All right, so I've been talking very abstractly kind of about NEXUS in general, roughly what it does to give you an idea, but what's it like to work with it. So on installation, I've tried to keep things very simple. You can just clone the QMC pack repository. It's packaged directly with QMC pack. Just note your path to the NEXUS directory in QMC pack. The installation is really just setting two paths. One, a Python path to the library of NEXUS module files, and one, a path to binaries for NEXUS. Once you do these two things, and say you have NumPy in addition on your system, you should be ready to run NEXUS directly. And given that this is fairly simple, you can do that most places, and you can test your installation quickly with this binary, which should be in your path now, Nexus test, and within a few seconds, you'll see that all the tests pass. Okay, so what's it like to compose workflows with Nexus? So this is the user script I've been alluding to in Python. So this is a very simple workflow, just doing a quantum espresso calculation followed by orbital conversion and VMC. So the header of the script, you just invoke the Python interpreter, which is common in all Python programs. You have a number of import statements from the Nexus module. So a function to give Nexus settings, to specify what jobs you want to run, and a function to run your project, and then the input generators come next. Well, I should say one to generate what physical system you're running on, whether it's Diamond or a molecule or whatever else, and then input generators for PySCF, the conversion code, and QMC pack itself. The next portion is user settings. So for example, you might point to where all of your pseudopotentials are located. You tell what kind of machine you're on, in this case a 16-core workstation. I'll cover in a moment how you'd specify a more advanced machine, a supercomputer. And you specify that you want polling or job monitoring to happen every 3 seconds with Nexus. Again, we'll see that in a moment. You specify the physical system once, and it's shared by all of the codes. For example, this is how you can input by hand the diamond structure. So you have the primitive cell axes, 2 carbon atoms at these positions. Nexus also handles more complicated structural operations that you might want to do in QMC, such as tiling. For example, this is the primitive cell, but say you want to do a 2x2x2 tiling, you would say that here, or you could supply matrix tiling, and one of the examples supports this, and supply, say, a one-course pack set of k-points for that supercell. Then this physical system is just passed to each of the different calculations that you're going to do. So these, for example, are the inputs for quantum espresso. This for PW QMC pack, and this for QMC pack itself. This is composing the workflow that you want to do. You can see that you actually don't have to put in a whole lot of information to specify what you want. It's pretty minimal. You say what prefix you want the files to have, where you want them to run, what kind of job you want to have. In this case, run it on 16 cores with MPI. And then the rest are inputs directly to Quantum Espresso. You recognize these keywords are just like our keywords from Quantum Espresso. Input DFT, ecut wave function, convergence threshold, no symmetry, WF collect. In fact, you can put any keyword supported by the QE input file here. Similar, I won't go into detail about PW QMC pack, but it's pretty simple. For QMC pack itself, if you want to run a slightly different job, say 16 cores, now with 4 OpenMP threads, you're going to pass the physical system in. Here you're running with a BFE potential, no Jasper factors, and then you just specify a simple VMC block with, this, again, keywords that are familiar from QMC pack. One important note is that these simulations depend on each other. This one needs to get information from the SCF run, and so it will run afterwards. And this one needs to run after the conversion run. At this point, all we've done is composed what workflows we want Nexus to run. No actual execution will happen until the very end. So you can add a for loop here to do scans over different parameters and various other things. But no execution actually happens until the script enters this run project function. Okay, so what does it look like to actually run this? So user script execution. So for example, before you run, you might want to see what kind of workflow you're running. So you can do that just with the command line setting, and it will plot for you the workflow that you're going to perform. In this case, just SCF, followed by orbital conversion, followed by VMC. You can check your initial run status by passing in a status only flags. That will show you all the directories that you're going to run in and the different identifiers that will show up in the jobs queue once the jobs are submitted. These are just a few status flags about progress that Nexus does for each simulation. The important one, though, is this flag here that's currently 0. This will tell you if Nexus has detected failure with any of your jobs. And then the job IDs will go in the dash sections once they're submitted. Okay, so to actually execute the script, you just run it straight, and you'll see that it starts off and shows an elapsed time. At the beginning, it goes into the SCF directory and executes this, which is MPI run, pw.x. You'll notice this is the familiar invocation to run Quantum Espresso on a workstation type machine. And then it goes into a polling phase. We set the polling frequency to be every 3 seconds. In between, Nexus will sleep and then wake to check on the status of your jobs. On a workstation, it's fine to do this frequently. On a supercomputing environment where you'll be checking the queue, you might want to make this a little bit longer, like 5 minutes, so that it consumes very few resources in between. But after just a couple of seconds, Espresso job is finished. It then executes the conversion step. After just a couple more seconds, that's done, and you go directly to the QMC pack submission. And after about a minute, the whole thing is done, and it tells you the project is finished. You can check the status at the end. It shows that everything's run successfully. It's completed everything, and nothing has failed. And then you move on to processing the results. In this case, just working at the command line to extract total energies, or using QMCA to get the local energy from QMC pack. Okay, so this is all on. This is all on just a workstation, like the AWS instances we'll be looking at today. But what do you have to do to change things to work in a supercomputing environment that has batched job capabilities? Okay, so here are settings for a workstation. You see here's a 16-core workstation. The job you provide is appropriate to that. I want this specific job for QMC to run on 16 cores with 4 OpenMP threads. And it will generate the 2 calls necessary for that. It will set the number of threads and do an MPI run execution for QMC pack. How about an institutional cluster? So, for example, CADES at ORNL, you just give the name of the machine directly. Often these machines require an account to run, so you specify that up here. And you specify a job that's very similar to the previous one, except now you want to run on 4 nodes at the same time and run for 8 hours. And it will generate this PBS submission script for you for that run. This is something that you now don't have to bother with. You just need to supply a little bit different information, and it will automatically populate everything needed to run on CADES and submit the job. Similar, if you're on a much larger machine, say for a production DMC run, like on Theta at ALCF, you provide that you're on Theta, the account name. Now, say you want to run on 1,000 nodes and 64 threads. You have a very small change in the Nexus input, but it does everything needed to run on Theta. Okay. One final capability that I'll note that's probably going to be useful in these kinds of environments is job bundling. So you can bundle together a bunch of different calculations at once to have it submit as a single submission. So what does that look like? So on Theta, for example, you just import this additional bundling function. Now I'm imagining that I'm doing something very simple like an equation of state in Diamond, where you now have a loop over different scaling factors. You're taking the Diamond physical system and you're rescaling all the coordinates by some amount, 90% compressed, 10% expanded, and values in between. Each time you have a QMC pack run at a different location, and you want each of these to run on 512 nodes. Well, what you do is you can just collect them in a list and pass them to the bundling function. And instead of 5 different jobs that will execute separately, you'll get a single batch submission script on 2,560 nodes with 5 different submissions that will happen at the same time. So you can widely populate the queue if you wish to. Okay, so are there any questions to this point? Go ahead, Josh.
Jaron, some time ago, the module environment on some of the big machines were, I believe, was like hand-coded in the machine specification in Nexus. Is that still the case, or is there a better way of doing that now?
Yeah, so the question was, Josh noted that at some point in the past, some of the imports, the modules that you load in the supercomputing environment were hard-coded into Nexus, and whether there's a better way of specifying that now. Yeah. So now we don't specify any module imports by default. You just pass in one additional keyword to a job, which is presub, and you can supply a text block with all of the different modules you want to load, and it will pre-populate that into each batch submission. So however you built whatever code, you just supply one additional keyword, and it will set it up. Okay. Any other questions?
So each machine has its own parameters where you define how to submit. So any new machine you need to modify NEXUS to contemplate that machine?
Yeah, so the question was, each machine has its own implementation in NEXUS, so the question is, do you need to modify NEXUS to handle each additional machine? And the answer is, to some degree, yes. Often these machines have a lot in common. For example, you query the queue with the QStat function, and it prints outputs in a particular way that you then parse to tell whether a job is progressed or finished or whatever. So NEXUS shares that part of the implementation as much as it can. So primarily new machines, you're just specifying how you populate the header of the submission file, and that does look different on different machines. And to be fair, these machines often will use common submission environments like Slurm and things like that, but each particular site have their own administrators which mess with the little script and change how it works, and so you actually do end up needing to specialize for each one a little bit, but it's not very much. You're basically just saying how the header needs to be written, when you're querying the queue with QStat or similar, where the fields are located and what they mean. So it's pretty brief.
Actually, so if I'm running on a generic workstation that I happen to own, so there's no queuing system, what sort of edits are needed to use all of that?
Should be none. So NEXUS can work generically on a workstation that has one core to say 128. It assumes that the submission that the MPI submission script is MPI run, and it will automatically do that. You can specify jobs to be serial and not use MPI run. It will also act as a virtual queue on a workstation. So if you have 16 cores available and you're submitting a bunch of jobs that are 1 and 4 cores, it will act like a virtual queue to populate all of those cores and keep them busy. But no changes are needed for workstations.
So I guess, let's say I have 2 jobs. One that is requiring a very small number of nodes because the scaling is poor of the code, and then sent to QMC. But I run them in 2 different machines. So this is still a case where I still need to transfer data from one machine to the other to be able to. NEXUS cannot send data back and forth.
Yeah, so I should have been more explicit about this. So the comment is that when you're working on multiple machines, say a workstation and then maybe a cluster and then some supercomputing environment, you still have to shuttle some data between the file systems on those machine environments. The NEXUS does not do this. That's true, but it's much simpler to do with NEXUS. So for example, you run on a workstation, you do some calculations to a certain point. You simply use rsync to transfer all of the files which are in a single directory from NEXUS over to the next machine with the exact same script. All you do is change the machine, like I showed in those previous examples, and run the script again on that new environment, and it will submit the jobs for that environment. So yes, you're just doing a single data transfer of what you have to the new machine, or back again, usually via rsync or similar. But it keeps everything simple. Okay.
When a job fails, tries to resubmit it by default?
Okay, so that's a very good question. So then, does NEXUS handle faults and try to recover from them? So this is actually a pretty complicated topic. This is something that say the materials project spent an awful lot of effort in doing. And I'd say it's very non-trivial in general because codes can fail all kinds of ways. And I'd say QMC codes can fail all kinds of ways. So it is in general difficult to say, okay, detect exactly what happened, and now also decide exactly what you need to do to correct, anticipating what the user's original intent was. So in principle, yes, this could be done, but I found it's complicated to the point where you don't want to try to do it. So it will notify you that something has gone wrong. For example, the variance is huge in your wave function optimization, and will flag it as failed. But then it's up to you to say, all right, now I want you to do this differently, rerun this job differently. But it's not so hard to do, right? You just copy one of these input blocks down, change it a little bit, and rerun. Okay, so it doesn't automatically correct for errors at this point. No magic.
There's no block write the paper, right?
Well, I mean, that's preferable.
No. So I haven't managed to write prl.exe with Nexus yet. No. So, other questions before we look at the examples?
So again, in the same sense, imagine this situation where I run Nexus on the same directory on my laptop, and I run the same Nexus on the supercomputer, but all the dependencies in the supercomputer are not met yet, so every 3 seconds it's still waiting because they're running on my laptop. When they finish, I just transfer them. Is Nexus able to pick up that now the status has been updated on the jobs and just start running from there?
No, you need to kill the Nexus. Oh, sorry, to repeat. So imagine you're working in kind of a pipeline fashion where you have some jobs running on your workstation and some that have been finished you've transferred over to a cluster, and you're running in both places at once. Can you just copy over updates from the runs directory on your workstation to the cluster, and will the running script on the cluster automatically detect that and continue on? Okay. The answer there is no, but Nexus scripts are interruptible. So if you're running on a cluster, for example, that's monitoring the queue, there'll be no side effects if you kill the running Nexus script and resume it to begin monitoring again. So in this case, what you would do is you'd kill the running script on the cluster, you'd copy the results over, and you'd simply execute it again. And then it would incorporate all of the new information by doing a recursive walk over all the directories that you've now newly incorporated there.
Implemented in a state machine library, or you code it as
So I developed Nexus. Okay, could you be a little more specific so I
well,
understand the
state
question?
machine is this way of computing in which basically your state changes according to certain conditions, and you go from one state to the other. Some conditions met, otherwise you go to some other state, and then you can jump between states. It's quite difficult to program in a procedural sense. It's very easy to make mistakes.
Okay, so some of the question is, how is Nexus designed? Does it operate in a state machine fashion? What's kind of some of the underlying design principles? So Nexus is written in object-oriented Python. So the objects do track state. For example, if you run a simulation workflow, it will track state in files located in each directory that say what the status of each job is and whether it's been run before. So when you come back and you've added a couple of blocks of recalculation or something and you run, it will read all of the workflow state from disk and say, okay, this is all the things I have done, these are the things I haven't done, and it will continue. But each execution of the script is a new generation of all the objects associated with it, and some of them load some state from disk. Okay. All right, if there aren't other questions, let me give an overview of the workshop examples. Okay, so if there's time now or during the breaks.
40 minutes.
Okay. Okay, so maybe we'll go into more of an interactive session here. So go ahead and navigate, if you're interested, to the GitHub repository for Day 2 Nexus. In there, like many of the other examples, are README files. These are best viewed through your browser. It will give you a much better rendering of the examples. These are all in long form. This is the Nexus directory in the workshop. I've written examples for VMC and DMC workflows for QMC Pack, starting from Espresso, from PyFCF, and from quantum package. All of the examples are standalone, so you can basically jump in at whatever point you're interested in and try it, whichever code it is or whichever example it is, you can probably start there at just your point of interest. But if you're new to Nexus, I would advise you to consider trying the first two Quantum Espresso examples, because there's even more discussion about Nexus in general and how it operates, so you can get more familiar with it. Okay, so the first set of examples are with Quantum Espresso. They're just in the Quantum Espresso directory. There are 4 examples. The first one is running a diamond primitive cell using a single, just a single DFT calculation with Quantum Espresso. This is kind of hello world for Quantum Espresso and Nexus. And then we build up more complicated examples. So the second one is how to do a matrix-tiled diamond supercell. So you're doing a matrix tiling from the FCC primitive cell into an 8-atom cubic supercell, including SCF steps to converge the charge density, a non-self-consistent calculation to calculate exactly which orbitals you need to populate the supercell, orbital conversion, Jastrow optimization, VMC. Example 3 is again in the matrix-tiled diamond supercell, but adding the steps you need to do twist averaging, say in VMC, but the same applies to DMC equally well. And finally, the fourth example is in the matrix-tiled supercell to do DMC. In all of these examples, the slowest steps, true to form, are the Jastrow optimization and the, say, diffusion Monte Carlo steps. So be prepared to be a little bit patient. Each of those steps will take a few minutes. So that's it for Quantum Espresso. For PySCF, these are located in just the PySCF directory. Similarly, a very simple example to start off, just the water molecule with restricted Hartree-Fock, just using PySCF. We have kind of 2 classes of examples. One are molecules, the other are periodic. So in the second example is how to do the diamond primitive cell. Again, just a single restricted Hartree-Fock calculation with PySCF. In example 3, we expand on example 1, now adding what you need to do more or less production quantum Monte Carlo for this system. So adding electron nuclear cusp corrections to the Gaussian orbitals, 2-body Jastrow optimization followed by 3-body Jastrow optimization, VMC and DMC. Then in example 4, going back to the diamond supercell. So this is just a small 2x1x1 tiled supercell, but adding the steps needed to do Jastrow optimization, VMC and DMC. And it's different basically in the K points that are needed for in PySCF to get that supercell. Okay, finally with quantum package, examples 1 and 3 are identical to PySCF, so you can kind of contrast the 2 codes there. The Nexus scripts are very similar, but the 2 codes are very different in their philosophies, but your experience should be about the same. As a second example, we look at the spin polarized oxygen dimer, where you do restricted Hartree-Fock, selected CI calculation, a calculation of the natural orbitals from selected CI, followed by a final selected CI calculation in the basis of the natural orbitals. And then in example 4, starting with this and expanding it to add the quantum Monte Carlo steps, adding nuclear cusp corrections, 2 and 3-body Jastrow optimization, and VMC and DMC. Okay, how much time do we have remaining in this block?
34 minutes.
Okay.
We have to hold it to it exactly.
Okay, so let's enter more of an interactive phase. For those of you who are interested, please just pick the examples you're interested in trying out. Start on them on your AWS instances, and if you have a question, comment, or run into a problem, just raise your hand, and I'll come over and work with you.
Thanks, Jaron.
Before you for example, how do you identify the dependencies? Okay.
So, first,
Okay, so the question is, specifying the dependencies between the calculations was subtle, and is it implicit or explicit, and how is it specified? Okay, in this case, it is a little subtle, but it is explicit. So it's through this dependencies keyword. So this generation function produced an object called SCF, and you start by saying PWQMC pack depends on SCF for orbitals in this sense. And Nexus will process the information needed to pass that dependency in between. So first of all, it will run this first and run this second as part of the dependency. Second, it will basically give it a file path of where the orbitals are located so that this step can execute correctly. And similar here, you say that this QMC run depends explicitly on the conversion step for the orbitals. And again, it will give QMC pack the path to the orbital file that's generated. Or if you had been doing JASTR optimization, you give the
SCF dot.
Comma. Sorry, it doesn't render very clearly here, but it's a comma. So yeah, much more complicated workflows can be constructed in this way. You can see that in some of the examples. So for example, this is what you actually need to do to get from restricted Hartree-Fock to DMC for the water molecule. These are actually all the steps you'd have to do yourself. But just by writing it out pretty simply in the Nexus file, it will take all of these steps. Okay.
Is there a way to put in like a dependency, but it's like not a real dependency? You just want one job to run like later than some of the other parts of it, a calculation? Like it's not actually taking anything from, yeah.
Yeah, there's a way to do that. So let me go back. In place of, so first I'll restate the question. Is there a way to introduce a dependency between two calculations that's kind of a fake dependency, that no information will actually be transferred between the two, but they will just run in that order appropriately? The answer is yes. And how you specify that is as before, you give the name of the object that represents the simulation, but in place of orbitals or JASTR or the specific thing that refers to information, you write other. And that will introduce a dependency between them.
Okay, thanks.
Any other questions? All right, so we're going to interactive mode.
Okay.
Jaron. I guess I'll just. So we talked about using Nexus on supercomputers, right? And this obviously is going to require leaving the Nexus script running on the head node. And some places make it awkward to leave something running, or they don't let you run for very long and then kill it. So how should we operate in that case? Just maybe have a job that runs the Nexus script every few hours, something like that, to get an update?
I'd say you've got three options in that case. I generally run Nexus interactively through the head node for a long time. I haven't run into problems with administrators personally, and this is the reason why. So for example, you can run with a long polling delay. So say 5 minutes, that's the sleep keyword. And what that will do is Nexus will, at the beginning, submit all the jobs, and then it will sleep, meaning it uses no resources on the head node at all, essentially 4 or 5 minutes. And the process will wake. It will use something like 2% of resources on the head node for a second or two, and it will fall asleep again for another 5 minutes. So that's one approach. Another is that you can run the Nexus script, have it submit all your jobs. You can kill the execution of the script, come back at any point later, run the script again, and it will simply resume its monitoring while you're there. Or the third option is to do what you just said, which is to have your own cron type job or something that will submit, run the script every hour or 5 hours or something.
Job every few hours.
Every few hours, and then immediately kill it thereafter. I think that would be similar to the sleeping process method, but either way, I've run Nexus scripts overnight, over the weekend, and things like that, and haven't run into any problems personally.
can we invoke Nexus and just script and just say, just do the next thing and then quit?
Yes, but that's more in,
Oh, 3 probably.
well, it's in these, you specify a keyword in these to the simulation that says block equals true. And that will say, don't do this or anything that depends on it. Some of the examples are set up this way, where you'll proceed through the first few steps. The script will shut down, and then you'll go into the script and edit it and say, okay, just comment out these block statements. Now do these ones, and then they'll run it. That's the easiest way to do that.
That's it.
I think it's a flag that you can also tell it to not monitor. I've used that where you just run it and it'll just do the next thing and shut down.
Yeah.
I can't remember the flag though, but there's some flag that you don't have to add in anything in those. It's just
There is. It's less well developed. It's easier to have explicit controllers saying what you want it to. If you want to have that type of control, you say run this into this. Run.
So if you'd like to modify your code and add new statements that aren't in this package, well, to have that Nexus.
You mean that would be such as would be reflected in, say, new input
file.
keywords in the input file? Yeah, the inputs are generally very easy to extend. So, for example, with Quantum Package, the implementation of the inputs in Nexus is just a list of the keywords.
Okay.
So you would just add keywords to the list, and then Nexus could handle it.
Okay. Related question, but different. Is there error checking on those keywords then? Let's say you misspelled a keyword.
So, yeah, misspellings will generally be detected, or some of them may result in a crash at points, but there should be error checking on what keywords are allowed and what are not. It does not always do detailed checking on the values you provide. So some of the responsibility does still rest on you to provide reasonable values for parameters.
These examples you're putting in like position angstroms. I mean, whatever you want to put into the last one.
Oh, yes.
Or space group equal points.
Okay, so I probably should have spent a little more time on how you specify the system because there are many more options than what I showed here. That's probably more convenient much of the time. For example, instead of specifying all the coordinates yourself, you can point to a postcard file or an XSF file or even a CIF file and start from there, and it will just load in the coordinates for you. For a lot of people, that will be the easiest way to work rather than rewriting it all in this type of a format.
You might mention there's the Nexus manual online, which probably has more information. Maybe it's pointed to what the readings.
Oh, yes, I'm sorry. Actually, I skipped my last 2 slides. So yes. Oh, yes, thank you.
Oh.
Okay, yes. Thanks for the reminder, Paul.
Let me just
So-
get out of the screen.
So for additional resources, where you might go, first of all, the reference paper, here's a link to it. It has more information about how Nexus is designed particularly, and please do cite it if you use Nexus in your work. Other places to go are the Nexus manual, which is linked here. It's about 50 or 60 pages of documentation and examples. It doesn't need to be expanded, but that's what we have for now. Nexus also features extensively in 3 of the labs in the QMC Pack manual, so you can get more experience going through very detailed tutorial level labs there. We also run a regular users meeting telecon via BlueJeans. So you can go, there's a GitHub repository for that. You can go directly there and get additional materials from each meeting on a topic. The README file at the head of the workshop directory for Nexus spells out more detail about what each prior meeting has been about and where the slides are for that meeting. Please also, you can consider attending the meeting if you're interested in Nexus. Just give me an email or post on the Google group or QMC Pack, and I'll provide information to you on how you can join that meeting. And probably just finally, I'll note some future directions. So we need to expand features in a couple of areas, specifically, targeting orbital optimization or the targeted excited state workflows. AFQMC is a big gap at the moment. This functionality is new, but I anticipate in the next couple of months to be able to have Nexus support for it. In the near future, we're going to have a more expanded example set and function level documentation. So for each of these generate functions, just documentation listing all of the possible keywords for each of those. Finally, in the future, we're going to be moving to Python 3. Everything in Nexus is currently Python 2. But as some of you may know, many major libraries in Python will sunset Python 2 support starting in 2020. So there'll be a move to move the whole code over to Python 3. Okay, that's all I've got slides-wise.
Thanks, Jaron.